look at this chapter. This is chapter 24.3, which is PET scanning. So first of all, maybe you are wondering what is PET. So you have to know it here. PET stands for Positron Emission Tomography. So positron emission tomography is PET. So it's related to the emissions of the beta positive particles. So let's see more information. This is the starting of the notes. Radioactive traces. So the first point, a radioactive traces is defined as a radioactive substance that can be absorbed by tissue in order to study the structures and function of organs in the body. So from here, you can see something like this. We put a radioactive substance into the human body, for example. So the human body will absorb the radioactive substance, will absorb by the body tissue, and because of that, there will be radioactive emissions that happens, and there is a detector to detect that, and because of that, we can study the structures and functions of organs in the body. Okay, so second point, radioactive isotopes such as technetium-99m or fluorine-18 are suitable for this purpose because before we look at the reasons listed down here, so let's see what is meant by technetium-99m. So the M here means meta-stable nuclear isomer of technetium-99. Okay, so it's just an isomer of technetium-99 that is suitable for medical purpose. Okay, so the other isomers that we use here, the radioactive isomers, is actually fluorine-18. Okay, it's fluorine-18. Okay, so these are the two famous radioactive isomer that we use in medical study. And now let's see why we use these two types of radioactive isomer. Okay, so the first reason is written here. The first point, they both bind to organic molecules such as glucose or water, which are readily available in the body. So imagine that, let's say in our human body, where the cells need glucose as food and need water for metabolism purpose. So the glucose or water that are sent to the cells are at the same time having the radioactive isotopes that stick to them. So because of that, they emit positrons, they emit radioactive particles or radioactive ray. So we can detect the activities on how the cells use the glucose or water, or any abnormality in the human body, like tumor, which use up the glucose, so we can detect that. Now the next point, they both emit gamma radiations and decay into stable isotopes. Okay, so they are radioactive isotopes, so they emit gamma ray. So next point, technetium's 99M has a short half-life of 6 hours. It is a short-lived form of technetium's 99. So as you can see, when we have short half-life, so there is an advantage over here. So the patient is exposed to radiation for a shorter time. That is the advantage of having short half-life. So likewise, fluorine 18 has an even shorter half-life of 110 minutes. So when you see these two that have short half-life, so patients is exposed to radiation for a shorter time. So that is the advantage. So now let's move on to the next page. So on this page, you can see using tracers in PET scanning. So first of all, we look at the point here. Positron emission tomography, PET, is a type of nuclear medical procedure that images tissues and organs by measuring the metabolic activity of the cells of body tissue. So we have to know that metabolic activity of the cells require glucose, and we use radioactive isotopes such as technetium 99M or fluorine 18 that bind with the glucose molecules, and because of that, what happens to the glucose is detected by the machines. Okay, by the machines. And let's see the next point. A common tracer used in PET scanning is a glucose molecules with radioactive fluorine, so that is the fluorine 18 that we studied just now, attached, called fluorodeoxyglucose. Okay, so fluorodeoxyglucose is basically glucose plus radioactive fluorine, so we call it fluorodeoxyglucose. The fluorine nuclei undergoes beta positive means positron decay, emitting a positron, so that is beta positive particle. Okay, so recall back the radioactive fluorine, the fluorine 18 that we use, they are radioactive, and because of that there are emissions of beta positive particles. And what happened then you can see here, the radioactive tracer is injected or swallowed into the patient and flow around the body. Okay, so that means before you do the scanning, before the patients do the scanning, they have to take the radioactive tracers. So what is radioactive tracers here? So the radioactive tracer is this one, fluorodeoxyglucose. Fluorodeoxyglucose is the tracer. Okay, it's the tracer. So this one is the tracer. This is the tracer. Okay, now let's move on. Once the tissue and organs have absorbed the tracer, then they appear on the screen as a bright area for a diagnosis. Okay, so that means it is detected. Okay, it is detected by the machines. This allows doctors to determine the progress of a disease and how effective any treatments have been. Okay, so the doctor can determine how is the disease. Okay, so they are, they are measuring the metabolic activity of the cell. Through the study of the metabolic activity of the cells, then we can find out that whether the disease is getting better or getting worse. So next point, tracers are used not only for the diagnosis of cancer, but also for the heart and detecting areas of decreased blood flow and brain injuries, including Alzheimer and dementia. Okay, so this is the disease caused by the old people. Okay, so this one, Alzheimer, is the disease caused by old people. Okay, so Alzheimer is caused by old people. Dementia is basically the brain problems. It's the brain disease where they have memory disorders, they have personality changes or impaired reasonings because of this disease. Okay, now let's move on. Let's look at the work example over here. Write a nuclear decay for the decay of fluorine 18 by beta positive emissions. Okay, so beta positive is positron. So we need to know that positron take 0, 1. Okay, 0, 1. Okay, so from here, how are we going to write down the equation? So let's take a look. First of all, the first steps, work out what will be on the reactants and product side. So the reactant side, we have fluorine 18, which is here, fluorine 18,9, 18,9 fluorine. Okay, and then the products, we have beta positive, that is beta plus, beta positive positron. This is 0, 1 beta, 0, 1. Okay, now you imagine the nucleon number up here is remaining as 18, but the proton number decreases by 1, become 18,8. 18,8, so decreases by 1 because of the positron. So 18,8 is oxygen. Okay, it's oxygen. 8 proton number is oxygen. Okay, then we also have gamma ray also. Okay, we also have gamma ray. So why we have gamma ray? This is already written in the first page, where technetium 99M or fluorine 18, they both emit gamma ray radiations. Okay, so gamma ray radiation is just energy. It doesn't affect the proton number and the nucleon number. Now step 2, we have to write the nuclear equations in this way. So as you can see here, the reactants fluorine 18,9 becomes oxygen 18,8 plus positron plus gamma ray. Okay, so this is the equations that represent the nuclear decay. Okay, so let's move on. So on this page, we have annihilations in PET scanning. So first, what is annihilations? So we need to understand the words here, annihilations. So annihilation is actually the conversion of matter into energy. Especially the mutual conversions of a particle and an antiparticle into electromagnetic radiation. Okay, so for example, let's say for these situations, we can put example as the particle is, let's say, the positron, the antiparticle is the electrons. Okay, positron and electrons, they collide, and then the mass of the positron and the electrons is converted into energy as gamma ray. So you can see the picture here. The electrons and the positron, this is the particle and the antiparticle, they collide. Okay, they collide, and then it becomes gamma rays. So this is the process which is known as annihilation. Okay, annihilations. So let's see the first point here. When a positron is emitted from a tracer in the body, so the tracer that we mean just now, if you still remember, the tracer is called the fluorodeoxyglucose. That is the tracer. So where is a glucose combined with the fluorine 18. Okay, that's the tracer. Now let's continue. When a positron is emitted from a tracer in the body, it travels less than a millimeter before it collides with an electron. Okay, so positron is coming out from the radioisotopes, and after traveling for a short distance, it collides with electrons. So positron collide with electrons. So the positron and electron will annihilate, and their mass becomes pure energy in the form of two gamma rays which move apart in opposite directions. Annihilations doesn't just happen with electrons and positron. Annihilation is defined as when a particle meets its equivalent antiparticles, they are both destroyed and their mass is converted into energy. So this is the definition of annihilations. Okay, so from all this information, right, first we can see they collide, and then two gamma ray will move apart in opposite direction. So it's like this, okay, in opposite direction. One gamma ray move in this way, another gamma ray move down. Okay, so this is the annihilation of a positron and electrons to form two gamma ray photons. Okay, now let's move on. Okay, over here, let's see the next topic here. Positron emission tomography, PET scanning. Once the tracer is introduced into the body, it has a short half-life. Okay, short half-life. So try to recall back the fluorine 18 just now. The half-life is 110 minutes. So it begins emitting positrons, which is beta positive, immediately. Okay, so this allows for a short exposure time to the radiations. Okay, so the patient is not having long time or maybe long-term radioactive exposure. Okay, so a short half-life does mean the patient needs to be scanned quickly, and not all hospitals have access to expensive PET scanners. In PET scanning, positrons are emitted by the decay of the tracer. They travel a small distance and annihilate. When they interact with electrons in the tissue, This annihilation produces a pair of gamma ray photons which travels in opposite directions. So let us look at the picture here. So what you can see here is this is the patient. The patients, they have to get the injections, okay, injection for the radioactive tracer. Okay, the radioactive tracer that I mean is the fluorodeoxyglucose, which is the glucose that combined with radioisotope fluorine 18. Okay, then beta positive emission happens. Okay, so you see the picture here. So once injections is done, then the tracers will just move everywhere throughout the body, and there will have a lot of tracers which reach here. So what happened here, let's say there is a tumor here. So the tumor with cancer cell, so they use a lot of glucose. The metabolic activity is high over here, so a lot of tracers come here, and then beta positive emissions happens here, where the beta positive is emitted. So the positron is emitted, and then it collides with the electrons in the surrounding, and then gamma ray is emitted in two opposite directions. Okay, this is the gamma ray, and then there is the gamma ray detector which can detect the gamma ray, and because of that we can study the metabolic activity of the tumor over here. Okay, so this is the illustrations of PET scanning. Now let's move on. Okay, so the next topic here, 24.2.3, detecting gamma rays from PET scanning. Okay, now the first point, the patient lays stationarily in a tube surrounded by a ring of detectors, as you can see here. So this is the patient, this is the ring of detectors. Okay, now let's move on. The next point, images of slices of the body can be taken to show the position of the radioactive traces. Okay, so let's move on to the next point. The detector consists of two parts. So this is the detector, as you can see. All these are the detector. Okay, so the detector itself we put in two different names: gamma ray detectors in blue color, and we also have activated gamma ray. Activated gamma ray is in red color. So activated gamma ray detector is basically the detector that are exposed to gamma ray, as you can see here. So it is called activated gamma ray detector. Okay, now let's look at the information over here again. Okay, so the detector consists of two parts: crystal, scintillator. When the gamma ray photon is incident on a crystal, an electron in the crystal is excited to a higher energy state. So that is why we name it as activated gamma ray detector. Okay, because the electrons receiving energy and go to excited state. As the excited electrons travels through the crystal, it excites more electrons. Okay, so imagine there are crystal here, so there are electrons that are excited. Okay, and when the excited electrons move back down to their original state, this is called the ground state, the lost energy is transmitted as visible light photons. Okay, so imagine the electrons after reaching excited state, so they are at the higher energy level. Now it comes back down to the lower energy levels, and because of that, visible light photons is emitted. Okay, it's emitted. And then the second part of the detector is the photo multiplier. So they say the photons produced by the scintillator are very faint. So that means the visible light is very faint. So they need to be amplified and converted to an electrical signal by a photo multiplier tube. So this is like an amplifier, okay, an amplifier which make the signal stronger. Okay, so settle for this page. So let's look at this page, creating an image from PET scanning. Okay, so the first point, the gamma ray travels in straight lines in opposite directions when formed from a positron electron annotations. This happens in order to conserve momentum. Okay, so if you still remember the picture just now where the gamma ray is moving in two opposite directions, so this is the detector in circular shape. Okay, so why they move in opposite direction? Because they want to conserve momentum. So if you have momentum going forward in this way, then you will have momentum going backwards in the opposite way. They hit the detectors in a line known as the line of response. So this is the line of response, this straight line. The tracers will emit lots of gamma rays simultaneously, and the computers will use this information to create an image. The more photons from a particular point, the more tracer that is present in the tissue being studied. And these will appear as a bright point on the image. Okay, so that means it is bright if there are tracers. Okay, if there are more tracers at that particular point of study. An image of the tracer concentration in the tissue can be created by processing the arrival times of the gamma ray photons. Okay, so these are the informations on how they create the image. Now we look at the calculation part. Calculating energy of gamma ray photons. In the annotations process, both mass energy and momentums are conserved. So the gamma ray photon produced have an energy and frequency that is determined solely by the mass energy of the positron electron pair. Okay, so the energy E of the photon is given by this one, E equal to HF. Okay, so where H you can see down here, we learned this formula before in quantum physics. So the H is the Planck constants, F is the frequency of the photons, so ME, mass of the electron or the positrons, and then C squared is the speeds of light, you power to it. Okay, so you can just relate between the HF and the MC square. Okay, so this is where the mass change to energy, and then the energy will have this particular frequency. Okay, so now the frequency will be high because this is going to be the gamma ray, so high frequency. And then the next point, the momentums P of the photon is given by this formula, P equal to energy over C. So if you are wondering how is this formula coming from, so let's look at the de Broglie wavelength that we learned before. Okay, so let's do a quick revision here. De Broglie wavelength, we learned this in quantum physics. So we have lambda equal to h over p. So if I rearrange this, I make momentum as the subject, then I will get this. And then you know c equal to f lambda. So lambda equal to c over f. You can substitute at the bottom. So p equal to h over c over f. So p equal to hf over c. And you know hf is energy. So we get p equal to E over c. So this is from de Broglie wavelength. Okay, from de Broglie wavelength, we can get this formula. Now let's move on to the next page. So on this page, we have example. Okay, let's see this example. Fluorine 18 decays by beta positive emissions. The positron emitted collides with an electron and annihilate, producing 2 gamma rays. So A, calculate the energy released when a positron and an electron annihilate. Okay, so to calculate the energy release, what we need to know is we have to use formula E equal to mc square. Okay, so now the mass over here must be the mass of the electron and the positrons. Okay, so where it is 2 times 9.11 times 10 to the power of negative 31. So the positron and the electron have the same mass, and then multiply with 3.0 times 10 to the power of 8. This is speeds of light, and you square it. Okay, then we just use calculator. So 2 times 9.11. So you will get 1.64 times 10 to the power of negative 13 joule. Okay, so this is the answer for A. Now let's look at B then. Okay, B, calculate the frequency of the gamma rays emitted. Okay, so we use E equal to hf. Now we need to know that the energy produced, this is the energy produced by positron and electrons. So the energy produced by positron and electrons, at the end they become 2 gamma rays that move in opposite directions. Okay, so it becomes 2 gamma rays. Okay, so that means 2 photons. Okay, so because of that, when you use E equal to hf, we are going to divide the energy by 2, because if you see the question here, the question wants us to calculate the frequency of the gamma rays emitted. Okay, so the gamma ray emitted, so that is one of the gamma ray. So one of the gamma ray will take half of the energy, another gamma ray will take the other half. So the energy is hence 1.64 times 10 to the power of negative 13 divided by 2. Okay, so for 1 gamma. Okay, then the Planck constant is 6.63 times 10 to the power of negative 34, multiply with the F, and then we find the F, so divide by 2, 6.63, okay, so we get the frequency as 1.24 times 10 to the power of 20 Hertz. Okay, so that's the answer. And then let's move on to part C. Calculate the momentum of one of the gamma rays. So to count the momentum, we use P equal to E over C. So the energy again is half. So we take the 1.64 times 10 to the power of negative 13 divided by 2 again, and then divide by the speed of light, 3.0 times 10 to the power of 8. Okay, then we just count this, then you end up with 2.7 times 10 to the power of negative 22 Newton second. Okay, so in terms of two significant figure, this will be the answer. So let's say for this one also, I change it to two significant figure, 10 to the power of 20, and this one also, I change it to two significant. Okay, now let's see the next part. Okay, we have done everything here. Okay, so let's see. Now we have exam style questions, although this is not from Cambridge, but it is related to PET. Yeah, this is taken from AQA, as there is no past year question at the point when I do this video. So let's see. A patient is going to have a PET scan. A small amount of radioisotope is injected into the patient's bloodstream, and the patient is left to relax. The patient then lies on a horizontal table and is moved into the PET scanner. The scanner has many detectors positioned in a vertical circular patterns around the patients. State what is meant by a radioisotope. Okay, so they want you to define radioisotope. Okay, so radioisotope, you can write the answer in this way. So you can say it is a material with nuclei which are unstable, or which will decay, or which will emit radiation. Okay, so the second part, let's look at the question first. The radionuclide used in the PET scan has a physical half-life of 110 minutes. So 110 minutes, that means if you still remember, 110 minutes is the half-life for fluorine 18. Okay, fluorine 18 has the half-life of 110 minutes. So the radionuclide is excreted from the body with a biological half-life of 185 minutes. show that the effective half-life of the radionuclide in the body is about 70 minutes. So I have to say that this is not to be in our concern, as our syllabus doesn't require us to care about the effective half-life based on the physical half-life and biological half-life. So we are not going to care about this. Okay, let's move on. Okay, so next one. Discuss what might be a suitable length of time for the patient to relax between injecting the radionuclide and moving the patients into the PET scanner. Okay, so now let us look at the effective half-life over here, which is 70 minutes. Okay, 70 minutes. So if it's 70 minutes, so that means your length of time should be around 70 minutes. Okay, so you can put your answer in this way. Of course, timed, you can mention like lesser than 70 minutes. So since, okay, we can put our answer like this: since the effective half-life is 70 minutes, the time should be between 10 minutes to 70 minutes. So this is kind of flexible. So as long as you put the patient into the scanner before the half-life, okay, before the half-life, to get ready. Okay, now second point. So to allow the blood to carry the isotope around the body. Okay, imagine from the point when you do injections, then the blood need to carry the isotopes around the body, and then to allow the isotope to be taken in by the body part to be investigated. Okay, now let's move on. Part 4. Okay, the decay of the radionuclide result in the emissions of a positron. Two of the detectors directly opposite to each other are triggered as they each receive a gamma photon. Explain the process in which the gamma photons are created. Okay, so now let's see this part. So we can say, first point, positrons collide with an electron and result in annihilation. second point, or the mass of positron and electron is converted to energy in gamma photons. So the third point here is optional. Must be 2 photons traveling in opposite directions to conserve momentum. Okay, we have 3 points altogether and you will get a maximum of 2 marks. Now let's look at the next part. Okay. Figure 1 shows the head of a patient that is 0.2 meter across, placed centrally between 2 of the many detectors in a PET scanner. To determine the positron where the gamma photons are produced, between the detectors, the scanner measures the short interval of time delta t between the triggering of the first detector and the triggering of the second detector. Discuss for the detector's position shown in figure 1, the range of the values of delta t that the scanner must measure to perform PET scan on the head. Assume that the speed of the gamma photons in the head is 3 times 10 to the power of 8 meter per second. So first of all, we need to understand the questions in this way. So let's focus on this particular part, the delta t. Okay, delta t over here, delta t. Okay, so imagine, let's say I just assume that there is a tumor in the middle of the head. Okay, so imagine that if there is a tumor at the middle. Okay, and after that, the traces is taken by this patient, and then there is a positron that is produced, and then the positron collide with the electrons, and then gamma ray is produced in 2 opposite directions. So gamma ray is produced in this way and this way. So in this case, imagine that the gamma ray on the left will reach the detector at the same time with the gamma ray on the right. They will reach the detector at the same time. So because of that, there is no difference in the times. The delta t will be 0. Okay, so that will be the minimum value for the delta t. Okay, so let us write this down as the first point. Okay, so if the gamma photons are produced at the center of the head, they will reach the detectors at the same time, and hence delta t is equal to 0 second, and this is the minimum. Okay, now let's consider another situations. Let's say we have let's say the patient has a tumor at the site. Okay, so at the side of the head, somewhere near here. Okay, so let's say I put a cross there. Okay, so let's say the tumor is very near to this detector on the left. So again, this patient is taking the tracer. The tracer produces positron. The positron collides with the electrons, and gamma rays are produced in two opposite directions. And you can see that they will reach the detector on the left immediately, and it will take the longest time to reach the detector on the right. Okay, so in these situations, the time difference will be the maximum. Okay, so the time difference, as the left hand side one is immediately reach the detector, but the right hand side one will take the longest time, so the time difference is maximum. So let us write this down. If the gamma photons are produced at the side of the head, one of the gamma photons will reach the detector immediately, and the other gamma photons will take t equal to, okay, so we know that time is basically distance over speed, so I'm using that, distance over speed. So I'm talking about the time span for the gamma, which travel all the way by 0.2 meter, as you can see over here, 0.2 meter. So the gamma photon is traveling by 0.2 meter to the other side of the detector, and this is the speed. So I have distance divided by the speed. Okay, so 0.2 divided by 3 times 10 to the power of 8. So I will get 6.7 times 10 to the power of -10 seconds to reach the detector, and hence delta t equal to 6.7 times 10 to the power of -10 seconds. So of course the delta t here is basically the difference in time. So we have this time minus with 0, because the other gamma photon reached the detector immediately, the time span is 0. Okay, so because of that, we take this minus 0, then we get back this one. So that is the delta t, and this will be the maximum possible values. So this is the maximum. So when you have the minimum and the maximum, so basically now we have the range. The range of delta t is 0 second to 6.7 times 10 to the power of -10 seconds. Okay, so this is the whole questions.